I should say that right at the beginning that I think it's an appropriate talk for the seminar because, in a sense, quantum computing is Fourier analysis in the binary world. So, so the talk is based on a couple of archive papers. They're listed here on the cover page. It's joint work with two of my math grad students, Jingzhen and Qingzhong Liang. I have to say that they've been trapped at Duke for 2 years and they're looking to see the world. So if you have an opportunity for them to visit, they'd love to hear from you. Oops, why is this not advancing? It is now. All right, okay. Quantum computers, they're moving out of physics labs. They're becoming generally programmable. What you're looking at here is an image of 80 ions held above the surface of an ion trap that was fabricated by Sandia National Labs. Chip's about 10 millimeters on the side. It's used by the experimental teams at Duke and IonQ. I should say this is actually a particularly good talk for the Maryland seminar because IonQ is a joint venture of Duke and Maryland. It's the startup company founded by Chris Monroe and Jung-Sang Kim, and it IPO'd last month. So it's the first, I think, publicly traded quantum computing company. All right. What's special about quantum computing? Well, what we're going to focus on in this talk is the challenge of quantum computing as that of engineering a protected space for doing a computation. In this talk, we're going to start from diagonal gates that play an essential role in important algorithms like magic state distillation, Shor factoring. And we're going to work backwards. We're going to describe how you might synthesize a protected space, in this case, a CSS code, in which the target logical diagonal gate can be implemented reliably. So that's the plan for the talk. All right. So first section, we're going to introduce the Clifford hierarchy. We're going to talk about levels in the Clifford hierarchy. We're going to assign levels to certain important diagonal gates. And we'll also talk about how to represent gates in the Pauli basis. So this is the plan. We, at the top, that's our target. We have a logical operation that we want to do. But we want to do it in a safe space. And so what we're going to do is we're going to take the logical information, we're going to encode it in a quantum error correcting code. We're going to have a physical gate, something that acts on the big Hilbert space, and it's going to induce the target logical on the logical information. So that's the idea. We want to implement this logical operation, this logical gate. We're going to do it in a quantum error correcting code. We're going to have some physical gate that acts on the entire space, and it's going to induce the right logical on the quantum error correcting code. We're going to reason about these logical channels using a mathematical framework called generator coefficients, which we'll introduce in a section or so. All right. What is a qubit? It's a two-dimensional Hilbert space. We use M-fold tensor or Kronecker products to describe M qubits. Single qubit, Pauli group P2. It's generated by bit flip X and phase flip Z. Pauli group on M qubits. So this is n by n matrices where n is 2 to the m. This is generated by matrices DAB. They're parameterized by binary vectors. So A and B, they're binary vectors. And they basically tell you how to make the matrix. So the A's tell you where you're going to put the X's, and the B's tell you where you put the C's, and you multiply them together, like shown on the slide here. And this is how we've got the states in the Hilbert space. There's 2 to the m of them. They're indexed by binary vectors V. This is how DAB acts on the state indexed by V. It translates it to V plus A, and it multiplies by -1 to the inner product of V and B transpose. The important thing about X and Z is that they anti-commute. XZ is minus ZX. This Pauli group is a group that's as commutative as it can be without actually being commutative. Two things in the group, they either commute or anti-commute. And which one happens is given by a symplectic inner product. This is quantum mechanics. We're particularly interested in Hermitian matrices. When is one of these Pauli matrices Hermitian? Well, it's easy to show that if AB transposed is 0, then DAB is symmetric. And if AB transposed is -1, then DAB is skew symmetric. So we can take a DAB and we can make it Hermitian by pre-multiplying by this scalar, I to the AB transpose. And I've written mod 4 to indicate that we're going to take the exponent modulo 4. So EAB is projection matrix, squares to the identity. So it's not a projection matrix, it's squares to the identity. It's got eigenspaces +1 and -1. Here at the bottom, Pauli group, I've just given an example to make things concrete. X Kronecker Z Kronecker Y, that's E101011. It's 1, 0 in the first position. So A is represented by a 1, B is represented by a 0, that's an X. Second position, it's the other way around, 0, 1, that's a Z. Third place, it's 1, 1, that's an X times a Z, which is called Y. There we go. Pauli group. Why target diagonal gates? Well, they play an essential role in magic state distillation, which provides a path to universal computation. Now, I'm not going to talk about magic state distillation in this talk. So, second reason is if you look at something like the Shor factoring algorithm, you'll see a little circuit in Nielsen and Chuang when they describe the Shor factoring algorithm. And you look here at the circuit, it involves a unitary operator U, which is the 2 to the Lth root of Z. So this is a diagonal matrix, and this circuit plays an important role in the Shor factoring algorithm. So it's an illustration that diagonal gates are really useful things. It's useful to be able to implement them reliably. What is the Clifford hierarchy? Well, at the bottom of the Clifford hierarchy is the Pauli group. The next level is the Clifford group. That's the normalizer of the Pauli group in the unitary group. And that's where the groups stop. From then on, the levels are defined inductively. So you're in the elf level if, when you conjugate the Pauli group, you end up in the L minus first level. Over on the right-hand side, I've looked at some diagonal gates. There's the phase gate, which is the square root of Z. That's a Clifford element. It's called P. CZ is control Z. So these things here, these guys are control operations. This is control square root of Z. And then you go up. The fourth root of Z is something called the T gate. And there's control phase, control code, control Z. You can see the pattern. So these are diagonal gates. They're all useful. And these are the diagonal gates that we're going to be targeting. So we'll do a little bit of Fourier analysis. So here, we can describe a diagonal gate just as a diagonal matrix. So we can, the entries of the diagonal matrix are indexed by binary vectors U, and I can tell you what the entry is in the position indexed by U. That's the DU description on the right. It's the description in the Dirac basis. The Pauli matrices that just involve Z's, they're also a basis for diagonal elements. And so I can describe a diagonal gate in the Pauli basis, and I can get from one to the other just by applying the Walsh Hadamard matrix. So that changes basis from Dirac to Pauli. So, all right, now then, I'm going to try and build up a little bit of intuition about codes and gates and how they work together. So I have to first of all tell you what a CSS code is. So it's defined by a stabilizer group. Stabilizer group S is a commutative subgroup of the Pauli group. It has the extra property that if G is in the stabilizer, then minus G is not in the stabilizer. Why do we do that? Because we're going to define codes as being the fixed spaces of stabilizer groups. And we can't have something being fixed by G and by minus G. That's not going to work. So that's the extra condition on a stabilizer group. CSS stabilizers have a special form. They're generated by pure X's and pure Z's. You look on the left-hand side here of this picture. This is my way of representing the CSS code. So everything on the left-hand side is a classical code. So C2, this describes the X stabilizers. G2 generates them. C1 perp describes the Z stabilizers. That's generated by this guy. All right, that's that. How do you make the CSS code? These individual terms, right? If you just fix on an individual j here, this term in plus this over 2, that projects onto the +1, projects onto the epsilon 0 dj, epsilon is plus or minus 1, projects onto the epsilon subspace of this operator. So this guy here, the constituents are the generators of the stabilizer, and this is a projector. And the image of the space under the projector, that's the code. So let's talk a little bit about CSS codes. Right, so as I said, the code space, stuff that's fixed by the stabilizer. Now, how does the code fail? Well, errors from the stabilizer, they fix the code. They don't matter. Errors that fix the space but don't act as the identity, they do matter. So, so bad errors commute with the stabilizer, and that's why we're interested in C2 perp and C1. And so here you've got things in C1, not in C2. This is the x distance. Here you've got things in C2 perp, not in C1 perp. That's the z distance. The minimum distance of the code is the minimum of the two. If that is d, then an undetectable error has to act on at least d qubits. Now, the original paper describing CSS codes focused on the code states. So it defined the codes by defining the states. This thing here, G, C1, C2, this is a generator matrix for the cosets of C2 and C1. And so here the logical information is getting encoded in this way. Here you've got a sum over the x stabilizers. We'll come to the vector y in a minute. So the vector y has to do with the signs that we attach to the z stabilizers. But most of the work on CSS codes since then has focused really on the code states rather than on the projector. We want to go back to the projector. So that's our perspective. All right, now then. So now I want to give some examples of codes and gates that fix them. My first example is I'm going to look at a gate which is a z rotation through an angle theta. We'll describe that mathematically in a couple of slides. And so this is a physical gate that acts on the entire space. I want it to act on the code as the identity, right? So I want the code to be a decoherence-free subspace. If the noise in my system were these z rotations, this would be great. I would have produced a code that doesn't see the noise. And this kind of noise is actually a characteristic of ion trap systems. So it's not an unreasonable model. A paper here at the bottom that I'm not going to talk about was necessary, where we derived necessary and sufficient conditions for this to happen. And the necessary and sufficient conditions I'll illustrate using the Shor code, the 1614 code. And so in the Shor code, the qubits are divided into clumps. So the horizontal lines are the clumps. The weight 2 Z stabilizers are defined inside the clumps. They don't cross clumps. So in a sense, the weight 2 Z stabilizers, they partition the qubits into clumps. So here we have 4 clumps. And the X stabilizers, they have weight 8. They're shown in pink. So these are the generators for the X stabilizers. The Z stabilizers, they exist on the horizontal lines. Gray means the sign is 1, and white means the sign is -1. Now, the rule for assigning a sign to a Z stabilizer is you take the inner product with this vector, which has half weight of the clump. So for example, this guy has this. So when I say this guy is 1, 2. 1, 2 has inner product 1 with Y, and so it gets a negative sign. This guy, 2, 3, has inner product 0, so it gets a positive sign. And what we showed was that if you had this clump structure, then and you sign things in this way, then stuff worked. All right. There's a whole. So in the last slide, the induced logical operator is the identity. In this slide, the induced logical operator is transversal T. I'm trying to do justice to a whole bunch of work, a lot of which involves Bravi and Ha. And what they do is they provide conditions under which the induced logical operator is transversal T. And so what are these conditions? They're conditions on the classical codes that define the CSS codes. And what they do is they prescribe the powers of 2 that divide overlaps between pairs and triples of code words. The important thing is that these things are all sufficient conditions. Let me not do them in too much detail. We've always, when we take this point of view that we focus on the stabilizer, we're able to derive necessary and sufficient conditions. We wrote a paper in 2020 that we were really proud of because it had this remarkable trigonometric condition. And it was weird. And what I'm going to describe today is, I think, a more intuitive physical condition, which is equivalent to the trigonometric condition, and which we can actually work with more easily. So, generator coefficients. I have to describe what they are. So generator coefficients are a way of describing channels. So what are we doing? We start out with an ensemble of states, rho 1. Describe it by a generator, by a density matrix. We apply a diagonal physical gate, UZ. Takes us to rho 2. We make a measurement. We end up at rho 3. And then we apply some kind of Pauli correction that gets us back to the original code. That's rho 4. And so in a sense, the logical channel is that which takes us from rho 1 to rho 4. what are the things that we have to worry about? Well, we have to worry about, well, how many syndromes do we have? And then within each syndrome, we have to worry about qubits in the code. What are the Z logicals? And so, our framework is going to be parameterized by syndromes and Z logicals. So I tried to say this in words. So we have, so we prepare a code state, we apply a diagonal gate, we use X stabilizers to measure, we apply a Pauli correction, and we get from row 1 to row 4 by applying some matrix B mu. So B depends on the syndrome that we measured. And and this operator B mu is a sum. So mu is fixed, the syndrome is fixed. We sum over the Z logicals. Where do the Z logicals live? They live between C1 perp and C2 perp. Here they are. And these guys, these A mu gammas, these are the generator coefficients. They're the generator coefficients that, that are determined by the diagonal physical gate. And that's what we need. So here's an example. So we start with the diagonal physical gate. Here on the left-hand side, we've expressed it in terms of the Pauli basis. And this is the generator coefficient. And what you notice here is that the diagonal gate was determined by these f of v's. And the generator coefficients are defined by averaging the f of v's. So these are the signs of Z stabilizers. So that's how everything is put together. Let's do an example. Such a nice example. So here, this is a Z rotation through an angle theta. That's what it is. When we expand it, we get this. What is f of v? F of v is just this. And now we're interested in the generator coefficients. Here they are. And on the first line here, we represent the generator coefficients as a sum over C1 perp. And then we simplify it to a sum over C1. How do we get from here to here? Actually, the way that we get from here to here is we use something from classical coding theory called the Mccullums theorem, or the Mccullums identities, which take a weighted enumerator of a classical code and rewrite it as the weighted enumerator of the dual code. And if you've played with weighted enumerators in classical coding theory, this will look like the sort of term that appears. I mean, you specialize the weighted enumerator by plugging in cosine and sine and I sine. And when we make this reduction here, if you pay attention to the exponent here, you can see that signs are actually quite influential. If somehow you'd engineered your code so that all of these guys had weight n over 2, then this term here would just be 1. And this would be a bunch of character sums. And the only one that would be non-zero is the one where this is 0. And this would correspond to the identity. And so this is the clue for how you make CSS codes that are oblivious to coherent noise. Here's another example. So in this example, we're going to have the same z rotation through theta, and it's going to preserve this little 422 quantum error correcting code. So here's how it's defined. The generator coefficients are defined in this way. Let's think about gamma being 0 here. So here we're summing these guys over C1 perp. C1 perp is a very simple code. It's only got 4 things in it. If I let me call this C and this minus IS, then for for the 0 vector, I get C cubed. And then for the vectors of weight 2, I get a CS squared. And I get to either sign it plus or minus. I sign it twice plus and once minus, and I get C squared plus S squared. Sorry, no, I get C times C squared plus S squared, which is C. This is this one, okay? This foreshadows the theorem that we're going to state, which is if we want the physical gate to preserve the code, we have to have this be true. And actually you can see visibly above that indeed it is true. We also keep track of the logical operator. The logical operator is just a z rotation through Satan. So that's that. And in one of the papers that we showed at the start, we proved this theorem, which is that your physical diagonal gate preserves the code space if and only if this is true. So this condition is actually equivalent to our remarkable trigonometric identity that we were so proud of. But we think that this is actually, I mean, what we're really doing here is we're requiring this operator B mu for mu equals 0 to be unitary. That's what this condition really means. And that sort of intuitively is why the code is preserved. We carry along the logical operator so we understand the logical operator is also defined in terms of these generator coefficients. So what should you, here's an example that I won't talk too much about. So here we have a physical rotation through theta. It preserves the Steen code, which is a one-dimensional thing. What it induces is a z rotation through some theta logical. Theta logical depends on theta. How does it depend on theta? Well, that's what this picture shows. So here we, this is the physical angle we implement, and this is the logical angle we get. So that's all right. So now we've defined, so we are particularly interested in things called quadratic form gates. Why are they called quadratic form gates? Because they're defined in a sense as a quadratic form. They're diagonal. But here you've got a matrix R, which is a symmetric matrix. It's got entries in the ring modulo 2 to the L. So if you're familiar with coding theory, things like codes, these look kind of suspiciously familiar, and they are. So these are actually quite interesting examples of diagonal gates, because one of the things that we showed was that all 1 and 2 local diagonal gates in the Clifford hierarchy could be realized in this way. If we want to check whether we're preserving a code, we can actually reduce it to divisibility properties. And what's the divisibility property? It's just shown in red here. It's just, we choose C1 and C2. So we choose where we can pick V1 and V2 from. We evaluate these quadratic form things. We evaluate them, over the ring, over the integers. And we want 2 to the L to divide. Now, this is actually going to be pivotal because, all right, so how do we raise the level of a physical gate that preserves a code? Well, you look at this divisibility condition and you could say, we need 2 to the L plus 1 to divide something. What could it divide? Well, if we replicated V1, like if we replaced V1 by V1, V1, and if we replace the matrix R by I2, by the identity Kronecker R, so R, R, then we'd get the right divisibility condition for the next level. So we can grow the physical level of a gate by concatenating, which is cool. So now I'm going to describe in the time that remains how we climb. So we basically have 3 climbing moves. And the first is concat. So actually, these are the 3 moves. The level of the logical operator is bounded by the level of the physical operator. So in order to increase the logical level, we're going to have to increase the physical level first. So concatenation, the blue arrow, is how we increase the level of the physical operator. And I think we'll talk in detail about how we go from 713 to 1413. Then once we've increased the physical level, we have to increase the logical level. We do that by removing Z stabilizers, actually making a bigger code. So we go from 1413 to 1422. And you say, oh, that's not so good because the distance dropped when you did this. And so the last thing is adding X stabilizers, which will increase distance back again. And so on the left here, we can go all the way from the 422 code, which you just saw, to a 6415-4 code, which is defined by Reed-Muller codes. All right. Concatenation. How does it work? So here, I'm going to show you pictures, and I'm going to hope that you're really interested and you'll read the papers. So, okay. So here we have a quadratic form gate. It's determined by a matrix R. And so on the left-hand side, we have our CSS code. On the right-hand side, we build another CSS code by concatenation. How does concatenation work? Just by taking tensor products. So 1, 1, tensor C1, 1, 1, tensor C2. How do we tensor our signs? It's just 1, 1 tensor y. And what we show is that the generator coefficient for tau r at the Elf level is the same as the generator coefficient for tau I2 tensor r at the L plus first level. So we start with a diagonal gate UZ, and we actually build one at the next level, which is like the square root of UZ tensored by itself twice. So in this way, we increase the level of the physical gate. Do we have an example? Here's an example. So the Steen code 713, it's fixed by transversal phase. We concatenate to produce 1413. That's fixed by transversal T on 14 qubits. Now the logical gates don't change. Before, it was phase dagger, and it's still phase dagger. So we can say, we have this lifting process. We can say exactly when something is preserved. We can say what degrees of freedom we have for design. Maybe I'll not talk about that. All right, so concatenation, that's where we've increased the level of the physical gate. Now then, we want to increase the level of the logical gate. How are we going to do that? Well, we're going to remove Z stabilizers to introduce a new logical qubit. Well, when we're introducing a new logical qubit, before the logical qubits were defined by C2 perp quotient C1 perp, and now there's one more logical, gamma 0. So this matrix doubles in size horizontally. And what's the calculus of these generator coefficients? We started off with A mu gamma, and that splits into two. There's an A primed mu gamma primed, and an A primed mu gamma plus gamma 0. And the two of them are, and we have the sum on the right-hand side. So when we remove Z stabilizers, we split the generator coefficients. Now there's something really, trigonometry is a very powerful thing. So what happens here is so in this particular case, the Steen code 1413 to 1422, you start off on the left-hand side with the generator coefficients, and they split. How do they split? They split in the way that's shown. What's really, you have this thing here about these being equal. You can see that they are actually indeed equal. And then when you're asking the question, do you preserve the code? So that's what it means to be admissible. Do you preserve the code? The necessary and sufficient conditions for preserving the code, for being an admissible split, is that on the left-hand side, that sum has to be 1. And so that's the sum of those two new generator coefficients. And in the example, it's exactly this trigonometric identity. So the double angle identity is just a magical thing. And it makes it possible to raise the level of the logical operator. Now, there are other ways of raising the level of the logical operator. And in the paper, we describe different ways of climbing. This is the double angle formula, but there's also Euler's formula appears. And also the recursive definition of the Walsh Hadamard matrix produces a way of climbing from j-1 control certain square root of z to the jth control of the same square root of z. So there's all sorts of incredibly beautiful trigonometric stuff that makes removing z stabilizers work. So that's two things. And now finally, there's the getting the distance back. And so here you have to add a new x stabilizer, x0. So x0 is in C1, not in C2. And that means that there's some z logical mu0 in the original code that becomes an x syndrome. So the starting matrix is short and wide, and the new matrix is wide and short because you've grown an extra syndrome and you've lost a logical. So when you introduce this new x stabilizer, you double the number of x syndromes and you half the number of z logicals. And so that blue rectangle just shifts from the horizontal to the vertical. And this works if and only if certain generator coefficients vanish. Which generator coefficients? The ones in D plus mu0. Well, what was D? D was the left-hand block in the left side. This guy. And the coset was this guy. So that works when here's an example. This is a calculus that works beautifully with the recursive way of defining Reed-Muller codes. So this is where we end up. This is where we start. This is an intermediate step. And the recursive definition of the Reed-Muller code says that this code is contained in that, and this code is contained in that. And when you make them equal by removing z stabilizers and adding x stabilizers, you move from this quantum error correcting code to that one to this one. And that's how it all works. So, conclusion. Yep. What would I like you to take away? Like you to take away that if I were to characterize prior work on codes and gates, it's all about sufficient conditions, not about necessary conditions. This framework does provide necessary and sufficient conditions. It also has the advantage of tracking the logical operator. It's induced by a physical diagonal gate. So it's very useful for analyzing all sorts of algorithms. This framework that I asked you to swallow in a short amount of time, it supports synthesis of a target logical diagonal operator by combining three basic operations: concatenation, removal of Z stabilizers, and addition of X stabilizers. Concatenation increases the physical level. Z stabilizer removal increases the logical level and the code rate. And the addition of X stabilizers increases the distance. I didn't talk about this in any detail, but if you had a system that was limited by coherent noise, then you could switch very quickly between computation and storage, and you could park intermediate computations in decoherence-free subspaces until you wanted to get to them again. All right. Thank you all for listening, and happy to